Hi everyone, my name is Lezhi Li, and today I'm going to talk about open source visualization frameworks at Uber. A little bit about myself. So I've been with Uber for 2.5 years, and my focus here is mostly on the intersection between visualization and machine learning. I also work with Uber's machine learning platform. At Uber, we ignite opportunities by setting the world in motion. And Uber's visualization team empowers creators with cutting-edge solutions for solving urban mobility challenges. So why we say so? At Uber, we consider visualization as a method for solving problems. So if you ask, if we want to solve problems, why we wouldn't use an automated system and use visualization instead? So actually, there are two types of unknowns. If you know what you don't know, you would solve a problem with an automated system. But if you don't know what you don't know, usually that process will involve human to be in the loop as well. So that's when you need to use visualization to solve a problem. And today I'm going to give 3 examples about how we achieve that. Basically, these are 3 different open source projects by the Uber visualization team. And they are visualization for geoanalysis called Kepler.gl, visualization for autonomous vehicle called Streetscape.gl, and visualization for machine learning called Manifold. First off, Kepler. As you know, Uber is a technological company, but business is tightly related to the real world. Our services generate millions of trip-related data records every day. And it's crucial for us to be able to see this data in a straightforward way and a performant way. That is the motivation behind Kepler. Kepler is a WebGL-powered high-performance web application for geospatial analysis. And Kepler is built on top of React. React is a JavaScript-based web framework, and Kepler is also based on top of some other Uber-developed WebGL-powered visualization frameworks that I will talk about later. So in order to showcase how Kepler works in action, I'm going to show this demo of inputting this New York taxi trip dataset into Kepler. So this is a dataset that contains about 300,000 trips. And as you can see from the columns include a timestamp column, and there's a geopoint column, including the beginning point and end point of the trip. There are also several metadata columns. As users drag and drop this dataset into Kepler, they can see basically the points for each starting and end point on this map. And users can apply this time-based filtering mechanism on top of this data set, which is purely done in the front end. And they can slide this time window to see basically at what time range did the trip happen. And the blue points represent the starting point, yellow points represent the end point. And you can apply additional user interaction to this map as well. For example, now you're seeing arcs connecting each starting point and end point of each trip. But however, if you show all the trips all at the same time, it's kind of messy. But we allow users to interact with this map using this brushing mechanism. So if you put a mouse on this map, you're only showing that, that any arcs whose starting point or end point is within a certain distance range from your mouse. And that way you can basically see the patterns much more clear. Also, it is great to be able to see each individual data points, but sometimes in order to show a more general trend and to eliminate outliers in the data sets, we kind of want to show this data in an aggregated fashion. So this aggregation in a hex bin, in this case, is also all down in the front end. And you can see that data points that fall into each geolocation is binned into hexagons, and you can adjust the size of the hexagons to show at different granularity. So within Uber, Kepler enables analysts to run analysis across a variety of scenarios. For example, we use it for incident investigation. Basically, if you apply the same type of time filtering technique, not to all the different data trips, but instead on the sensor record that's related to one particular trip, you can kind of reinvent this whole pickup scenario where this airport pickup happened. So in this instance, apparently this user reported that the driver did not pick them up at the first time they were at the gate of the airport. So we use Kepler.gl to reactivate, activate where the case where that car was and where the driver was to investigate what was possibly the cause for this missed pickup. Other use cases might be we want to investigate a traffic accident. We also use sensor data from accelerometers from your phone and geolocation traces from a phone to do this kind of analysis. And when we view data in aggregate, we can find patterns that are hidden inside of a data set. So this is a data set where we show the driver's rating after trips as related to the location where the trip begins or ends. So if you imagine you see this data set in the raw format and try to correlate the region and the driver scores, it's hard to parse what the causal relationship might be. But if you map this onto a map, then the pattern becomes apparent. So this is a London region. At the city center, the driver rating is much lower than the periphery of the cities. Here's another famous case done by my colleague. This picture depicts basically how congested each road segment become if all the trips are happened on separate trips versus the trips are combined trips using the Uber Pool product. If you know, Uber Pool is where you can, basically several drivers can be put in the same car so that we can reduce the total amount of trips and reduce the level of congestion we brought to the city. And basically this visualization really provides persuasive insights for evaluating the confidence level strategy and to evaluate basically the transportation strategy we want to adopt. So now I'm going to introduce a little bit about the technology behind Kepler.gl and particularly how we enabled such a large amount of data set to be processed in the front end. The key to success of handling large amount of data is leveraging GPU. And GPU allows applications to remain faster and responsive. We can compare CPU with a pipe where each computation operations happen in sequence. However, GPU is like a sift, and all the data points can be processed in batches so that the application is more powerful in handling large amount of data. So in what way is GPU helpful for this map application? GPU is good at batch implementation of multiple simple and repeatable computations at the same time with extreme high speed. And that aligns well with implementation of, for example, map projection. So if you consider map projection, really it's about you take a input data point, which is latitude and longitude, and you have a projection function which maps this latitude and longitude to a particular point on this canvas. And it outputs screen coordinates. And this computation is extremely simple, and it can be done on each of the data points at the same time. So that gives us a very good opportunity to leverage GPU. This is the implementation of using CPU versus GPU. In CPU, you write a JavaScript function which takes latitude and longitude and the viewport to produce the screen coordinates. However, in GPU, all you need to write is a vertex shader. So vertex shader determines the position of a point on the screen space based on its position in the geometric space. And it's automatically applied to all the data points at the same time. As you can see here, the geo position is determined by a projection function that takes an instance of projections and the viewport, which is a matrix. The interaction can be implemented using shaders as well. Interactions are really about taking a geospatial point and compute the distance between that point to your mouse position. And there's a Boolean that controls whether you show this arc or not based on whether that distance is within a certain range or not. And the implementation of that is vertex shader for brushing. The isPointInRange function is used to decide whether a point is within a distance range to the mouse. So this chart shows the stack behind Kepler.gl. Here are the stack of WebGL-based libraries that are all developed by Uber, and they're all used to support Kepler.gl. As you can see at the very bottom, Luma and deck.gl are the main packages that deal with WebGL-related operations, such as data binding and visual overlay rendering. So since we have already developed these packages, they could be not only used for supporting map applications such as Kepler.gl, but they're really general web-based rendering engines as well. So we can use them to support other applications actually developed by visualization team as well. So moving on to the next project that I'm going to talk about, this is also a project that leverages GPU. And this is an open source application that benefits WebGL. And it's designed to visualize self-driving car systems, Streetscape.gl. Like Kepler, it is also built on top of React and Uber's WebGL-based visualization frameworks. And it consumes data in the AVS protocol, which is a protocol that encodes autonomous vehicle data. And I'm going to introduce AVS protocol for a little bit. What is AVS? AVS is a server-side protocol for real-time transfer and visualization of autonomy data. So the purpose of it is to decouple the platform from presentation. As you can see on the left side of the image, you have the data source where it is a robot, in this case a vehicle, where all the sensor is attached to, or the data is recorded. You have this log system, and you record data from sensors, from the metrics in the car, and from the actions the car is taking, and put it in an AVS format. Next, you don't need to do all the things, particularly for one single visualization application. All you need to do is to convert it into AVS format. And the front-end application reads data from this format so that basically the data source and the representation can be detached from each other. So how does AVS help visualization? data specification of XViz is centered around objects, metrics, UI interfaces, and bindings. It is also time-based. So as you can see in this image, users can toggle on and off different data streams based on what type of information they want to see from the monitoring system. And that way, it's really convenient for this visualization system to represent objects and metrics. Here's the XViz data flow. And you have this data input from this live system and log. We have the converters and encoders to put them into the XViz format. Next, this data will go through our server that does product handling, and it can be streamed to the client side through either through real-time streaming or through static loading, like what you can record data and try to review them later. And in the client side, we have a decoder for the XViz protocol. And then at the very end, you have the declarative UI, which is the Streetscape.gl, to show what the information you want to see. So internally, Uber's advanced technology group uses XViz plus Streetscape.gl to enable log viewing, triaging, simulation, debugging in a web-based application. And the most frequent use cases is this comparison and debugging process. So Streetscape.gl allows you to see multiple simulations with varying parameters at the same time and compare them against each other. So basically, if you consider you have multiple simulations to run, each with a different parameters, and you want to optimize the system in a certain way. So each time you modify a parameter, it allows you to see the difference between the previous state and current state after your modification. So in that way, it's really easy for developers to see what the changes could be what changes in the system could cause on this car, so that we have better understanding of what's happening in the streetscape here. Another useful application is metric viewing. So as we mentioned earlier, Streetscape.gl, XViz not only records information regarding the objects, but also metrics on different objects. So here, if you see the metrics table pinned on top of each vehicle, these are actually sensor-sensed data that are recorded in real time during this during the simulation. So user can choose to interact on each of the objects and toggle on or off to see what information they want to see. Again, technology behind Streetscape. This one shows a various coordinate system at play with the data. So at a second level, on top, there's vehicle data. So this vehicle data is collected from sensors, which is their coordinate system is related to the vehicle. And at the third level, we have submaps, which is based on top of a geospatial system. And there's a base map. It's also a system that's based on top of some other application we request from the web. So all this different coordinate system needs to be combined on the screen. And at the very top, we also allow third-party customized metrics to be rendered on top of a streetscape. So all this rendering is done through WebGL, and basically each layer is considered as one shader. And this shader does this projection one by one on top of each other. So how does Streetscape work? Streetscape is basically using deck.gl and other WebGL-related libraries, as mentioned earlier. It has this powerful layering model. It simplifies mapping of different visual layers by using shaders to project on top of each other. And we add in hooks for interactions so that it can be more useful for the users. OK, so we have talked about realistic data visualizations. Basically, all the previous frameworks we developed were either geospatial data or robotic data, which is also something in the real world. And now I want to switch gear a little bit to talk about abstract visualization, or visual analytics, which is a technology to use visual support to analyze and find insights in abstract data. And particularly today, I'm going to discuss this Manifold, which is a package for model-agnostic visual debugging for machine learning models. And Manifold is built on top of React and other GPU-accelerated linear algebra libraries developed by TensorFlow. So we are leveraging the GPU-accelerated functionality from TensorFlow. Why is model debugging important? So machine learning practitioners usually report that the majority of the time is spent not on building the models, but instead on iterating on an existing model and try to improve their performance to an ideal level. And because they spend a lot of time on this iteration process, it gives us a lot of opportunities for us to improve the efficiency and clarity for them to do this iteration process to make this process more efficient. Before we had Manifold, the classical way for people to observe and evaluate models is through performance metrics. So performance metrics are this kind of scores that are kind of associated with a model. They are generally produced during training time. They are either area under curve for classification models, or, for example, root mean square error for regression models. Although the summary statistics are useful, they are not instructive enough for us to decide where to go from existing models. For example, I have Model 1 and Model 2, each gives me a score. I know which one is better than the other, but I don't necessarily know where to go on from there and how to develop a better model. Do I need to do more hyperparameter tuning, or do I need to do more feature engineering? It's quite unclear there. So since machine learning algorithms are intrinsically black boxes, there's an inherent complexity that prevents us from knowing this model from inside out. So given that condition, how do we understand model performance better? The idea here we're proposing is that we actually transform a model space problem into a data space problem. And by that, we mean that instead of looking at what went wrong with a model, we ask, on what data does the model make mistakes? We look into the data segments on which a model performs well or not well, and how it varies from model to model. Also, instead of looking at why a model makes mistakes, we look at the feature characteristics of failed data points. We look into the aggregated feature attributes of the data that they want to improve on, so that they can have a good idea, okay, these are the features that are causing the low model performance. So based on that idea, we developed Manifold. Here's an interface. It consists of two views, the performance comparison view and the feature attribution view. In the performance comparison view, data sets are automatically segmented into subsets based on performance and based on performance on each different models. And user can choose to group each subset to be compared against each other. And this comparison is shown on the right side, where you can see feature distribution histograms between these two segment groups. To dive deeper into this interface, in this performance comparison view, we have each row is a different segment. And each segment is, we call this violin plot, which is actually a distribution of a data subset based on its performance. So on the x-axis, there's a performance metric. So what this chart is showing is that the top data segment has the lowest log error, and the bottom subset has the highest log error. So it is sorted from better performance to worse performance. Also, since we have two models compared against each other here as well, you can see that in the first data subset, we have the green distribution that's shifted to the left side as related to the orange distribution. So that means that the green model, or the deep learning model, is better performing than the XGBoost model in this case. However, in the last subset, scenarios is reversed. The XGBoost model is better than deep learning model. And how do we actually split this data into segments? We basically compare the per data model performance metric. So this blue data set is a prediction output from one model. And we compute the prediction score of each individual data point based on the distance between that prediction and the ground truth. And if we have multiple models, we have multiple performance score columns. And using these columns, we ran a k-means classification, k-means clustering that segments all the data into several subsets, as shown in the animated image here. So jumping into the feature attribution view. Feature attribution view are actually two sets of feature distributions. One set is from group 0. The other set is from group 1. So the pink is a feature distribution of group 0, and it's compared against the gray distribution of group 1. And what this image tells us is that the top 3 features, since there's some offset between the pink distribution and the gray distribution, that means group 0 has distribution difference from group 1. However, the bottom 3 features, there's no much difference since these two curves are on top of each other. And to put it all together, here's a user workflow. Given the data set, which is an output from one or more machine learning models, Manifold will compare and highlight performance differences across models and data subsets. Users can then select data subsets of interest based on model performance for further inspection. And lastly, Manifold will highlight the feature distribution difference between the selected subsets, helping users to find the reasons behind performance outcomes. So now I'm going to give 2 examples of how Manifold is used within Uber for improving model performances. Case study 1 is about identifying useful features. So there's a team at Uber who is trying to evaluate the value of adding some extra features. So they trained 2 models, one with extra feature and one without extra feature. The 2 models gave similar performance scores. And there's no way for them to tell whether this new extra features were helpful for them because the scores are similar. They were asking, are these new features still worth adding, since adding new features in the system will definitely be more costly? So they used Manifold to evaluate this. They took these two models and input it into Manifold. And this image shows basically the performance distribution of 4 different subsets. And as they notice, although there's no difference on the second and third and fourth clusters, there's a significant difference in the top 1 cluster, where you can see the green model is actually towards the right side of the orange model here. So because cluster 3, which is the top one, the top cluster, happens to be the poorly predicted data segments, by that we mean that because cluster 3 is on the right side of the screen compared to all the other clusters. Because this segment were initially poorly predicted, actually the new model, which is the orange one, increased the performance of this segment. So their conclusion is that the new features did have some improvement on this hard to predict part of the data. So their conclusion, they should use the new features because they will make the most difficult to tackle instances easier for them. And case study 2 is about eliminating false negatives. A team at Uber is trying to improve their model performance, and they focus on reducing false negatives. So why is this so? Basically, they're trying to solve a problem where false negatives has more impact than false positives. Basically, for example, if you try to detect whether there's going to be a traffic accident happening, if there's going to be a traffic accident, but you didn't detect it, that's a really bad scenario. But if there's not going to be a traffic accident and you reported there's going to be a traffic accident, that's not so bad compared to the previous scenario. So they focus on false negatives. They ask the question of when a positive data point can be neglected by a model. The method is that first, they compared all the positive instances that's being captured and not captured by this model. Basically, they split the data set between the false negatives and true positives, and found out that the distribution between these two segments are actually different. However, given this difference, why is the model not being able to detect this difference and cause this false negative to happen? They further investigated, as a step 2, they further compared all the positive instances against negative instances. So if you see on the right side of the screen, the negative instances, which is the gray group, has lower values in these features compared to the positive group, which means that the instances tend to have lower values in this feature. Negative instances tend to have lower values in these features. However, if you compare the gray group on the right with the pink group on the left, they are more or less similar. And the pink group on the left are false negatives that we discovered previously. And what this means is that false negatives actually lack some of the characteristics of positives. And the way to solve this problem, as they came up with, is that since this model seems to be over-indexing on these key features, they should probably either find more features and/or train separate models where these key features are not so obvious in this data set, so that they can better distinguish between the true negatives between the false positives. And finally, I'm going to talk a little bit about the architecture of Manifold. In order to implement this idea in production, we encountered several challenges. There's a performance challenge, and there's portability challenge. So as we mentioned earlier, in previous world, we compute all the performance scores during training time. However, this is no more convenient for us to do in Manifold because instead of summary statistics, we also need to compute more detailed, more granular statistics, and we are going to allow user interaction. And this system needs to generate new metrics every time user interacts with the system, and that will introduce a lot of latency. Also, if you are going to plug another model training pipeline to the Manifold system, it's going to be hard because if the component for calculating the metrics lives in backend, we need to port out both the backend code and the front-end code to make that possible. But really, the calculation part actually belongs to the front-end part, so we prefer them to be grouped together instead of having to live in two different places. And those two reasons justify we put this numerical computation method component for visual debugging tool into the front end. Because this computation can get intensive as the data volume increases, we use TensorFlow.js to increase the computation efficiency. And with the help of TensorFlow.js, we were able to boost the performance of the UI system to a large extent. For example, if you consider k-means, in the order of 10,000 data instances, k-means was unable to run in a plain JavaScript implementation, but it runs quite smoothly with TensorFlow implementation as shown on the top right image here. So finally, these are different products I talked about today, and if you're interested in learning more, here are GitHub addresses for these projects. And Manifold is actually coming soon. We're in the process of writing more documentation before we're going to release it. And this is my team. This visualization team at Uber, they have a variety of skill sets ranging from front-end to computer graphics to information design, UI, UX design. With that, it's the end of my presentation.